Hello everyone, good afternoon. My name is Jen Gao from New York University, and this is a joint work with Steve from UMass, and Tan Bing is my professor, and Latent from Signify Research North America. So our topic is non-parallel emotional speech conversion. Here is my agenda. First, I will introduce the problem, and then give a briefly review of the previous work. After that, I will present our model and show some experiment results. There are many different tasks and applications in speech processing. I simply classify them into three different domains. First is the speech recognition, that is to use machines to analyze human speech. For example, extract the linguistic content, or detect speaker identity, or extract the emotional conveyed in the speech. The second is speech synthesis, that is to generate fake speech which is similar to human speech. For example, the text-to-speech system, TTS. In this category, the AI speakers may not have any emotion in it. The third one is voice transformation. That is to change the speech signal by different purposes. For example, voice conversion is to change the speaker's identity from one person to another. Accent conversion maybe mimic the accent of a native speaker. Our task is the third one, emotion conversion. That is to change the emotion part in human speech, for example, from neutral speech to emotional speech, or vice versa. There are two different settings in speech conversion, parallel and non-parallel. In parallel setting, people require the data to be paired. For example, in the left column of this picture, we can see the shoes on the left and shoes on the right. They have the same shape but different color. This is paired data. But in the middle column, we can see the pictures on the X domain and the pictures in the Y domain. They have different content. So this is unpaired data. For parallel approach in audio and voice conversion, people generally need temporal alien parallel data, and this data needs manual segmentation of the speech signal at phoneme level, and they require professional actors to pronounce the same sentence in different emotions. It's very difficult to collect. Therefore, the database generally has limited number of sentences. For example, less than 10 sentences in a database. For non-parallel approach, this is quite different because the data is very easy to collect. The model is very easy to train because they don't need manual segmentation, these manual operations. And the approach is easy to apply to real applications. Here is the related work on generative modeling. Given dataset, let's say X is the data, Y is the label, and Z is the latent code. Discriminative learning learns the model from data to label, that is a classifier. And generative learning modeling the full distribution of data Px or Pxy. Directed graphic models are the most popular one. It is to find the parameters theta such that the model distribution P theta is close to the data distribution. Variational autoencoders are framework for learning directed generative models. It is one of the likelihood-based models. The decoder PXZ describes how to convert a latent code into a data sample. In contrast, the encoder PZX describes the latent factors underlying a data sample X. Generative adversarial networks are implicit generative models, which do not explicitly specify a likelihood function like the VAEs. Instead, they brought two networks to compete against each other. A generative model G theta captures the data distribution, and a discriminative model D phi This screen distinguishes between samples from the generator and the real training set. Autoregressive models is a feed-forward model which predicts future values from the past. Any autoregressive model can run sequentially to generate new samples, but it's very slow. For example, the WaveNet. Related work in style transfer. Style transfer originally refers to rendering an image in the style of other images. But this idea can be used to other kinds of data like music, audio, and text. For domain-based style transfer, it modifies data from one domain to another. For example, style transfer can change photographs to oil painting, or change music of a piano to music of a guitar, or change printing to handwriting. For example-based style transfer, it can change the label of data by modifying a small part of it. For example, the adversarial attack can use adversarial eyeglass frame to attack face recognition systems. Or in natural language processing, people can add or delete words to attack speech recognition systems. Or people can modify stop sign as a speed limit sign in an automatic traffic sign recognition system. Emotion-related features. Previous emotion conversion approaches directly modify parameterized prosody-related features that convey emotions. Kawanami first proposed to use Gaussian mixture models for spectrogram transformation. A recent work by Xue explored 4 types of acoustic features: fundamental frequency, spectral sequence, duration, and power envelope. They investigated their impact on emotional speech systems and found dominant features are fundamental frequency and spectral sequences. They also claim that all emotions can be synthesized by modifying the spectral sequence only. Here is the picture of our emotional voice conversion model. It takes input of speech signals and output converted speech with different emotions. It is an end-to-end model. The features are extracted and recombined by word vocoder and converted separately. There are 3 different features: fundamental frequency, spectral sequence, and AP. F0 is transferred by log Gaussian normalization. Mu, sigma are mean and variance of the training set with domain I. And AP is mapped directly. Spectral sequence, which is the most important one, is learned by an autoencoder model. We will explain this model later. Let's review our task. This is to transfer the emotion-related characteristics of a speech signal by preserving the speaker's identity and linguistic content. In mathematics, we define samples from source domain as x1 and the target domain as x2. The model should learn a mapping T such that the semantic content is preserved during transformation. The generated output looks like that in domain x2. It is an ill-posed problem because for paired data, we know the joint distribution, and it's easy to learn the conditional distribution. But for unpaired data, we only know the margin distribution. Therefore, the conditional distribution cannot be directly learned. Therefore, we need to add additional constraints. Since we want to decompose style and content information, we need to investigate the disentangled representation learning method. In images, the low-level features like color, texture captures the style information, and high-level features like the category labels capture the content representation. And for music, the low-level features capture the timbre style, and the high-level features like melody, composition capture the content information. For speech, it is similar. The accent and emotion are lower level features, which is the style, and speaker identity and linguistic content are the high-level features. There are several types of tasks from high-level to low-level style transfer. Machine translation is to keep meaning of the source language and change the linguistic content. Voice conversion is to keep the linguistic content and change the speaker identity. Emotional voice conversion is to keep the linguistic content and the speaker identity, but change the emotion. We need to learn disentangled representations of style and content. People find data representations that independently model variations in semantic content and style information in several different data. For example, in image processing, the convolutional neural networks is a natural representation that can decompose the style and content. How about audio and speech? Unfortunately, this kind of data does not have an obvious disentangled representation, and we need to learn it. In the previous research, people find human emotion perception is a multi-layer process, so we use multi-layer perception model to extract emotion-related information in speech signals. And the emotion generation process of human speech follows the opposition direction of emotion perception. Based on these findings, we assume that first, the speech signal can be decomposed into an emotion-invariant content code and an emotion-dependent style code. The encoder E and the decoder G are inverse operations. Here is the speech autoencoder model. Our model has 4 subnetworks: E, C, ES, G, and D. For notations, we assume XI is the utterance from emotion I. EC, ES are content and style encoder. GI is decoder. CI and SI are content and style code. XI from J is the converted speech signal from emotion J to emotion I. XI prime is the reconstructed speech signal. C is the shared content domain. SI is the emotion-related style domain. The encoders and decoders are implemented with gated convolutional neural networks. In addition, a GAN model is added to produce realistic spectral frames, in which D is the discriminator in GAN to distinguish between real samples and machine-generated samples. There are multiple loss functions in our system. The spectral sequence should not change after encoding and decoding. To keep encoder and decoder as inverse operations, we apply reconstruction loss. In our model, the latent space is partially shared, but the cycle consistency constraint is not preserved. We apply a semi-cycle loss in the coding direction. Moreover, we add a GAN model to improve the speech quality. The converted samples should be indistinguishable from the real samples in the target emotion domain. So the GAN loss is computed between the real samples xj and the generated samples xji prime. Here is the picture of our multiple loss functions. The full loss is a weighted sum of reconstruction loss on data, semi-cycle loss on the content code, and semi-cycle loss on the style code, and the GAN loss on the data, where lambda x, lambda c, lambda s, lambda g are the weights. This problem is solved by robusted optimization. It's a minimax optimization problem. Here is the architecture of the network. In the content encoder, instance normalization removes the original feature mean and variance that represent emotional style information. In the style encoder, Emotional characteristics are encoded by a 3-layer MLP that outputs channel-wise mean and variance, mu and sigma. Then they are fed into the decoder to reconstruct spectrogram features. The desired emotion is added through an adaptive instant normalization layer before activation. Encoders and decoders are implemented with one-dimensional convolutional neural networks to capture the temporal dependencies, while the GAN discriminators are implemented with two-dimensional convolutional neural networks to capture the spectral temporal patterns. Higher resolution data is generated by the pixel shuffle layer in upper sample blocks. All networks use gated linear units to keep track of sequential information. Here is the detailed architecture. Here's the experiment part. We use non-parallel dataset EmoGAN. It has hundreds of sentences pronounced by different speakers. Entire data has 12 hours of script and improvised dialogues in 5 sessions, and it has background noise. We use the 4 most popular emotions: angry, happy, neutral, sad, to conduct our experiment. Our approach can also apply to other datasets like YouTube videos, movies, or user-provided audios. There's no limitations of our approach. We evaluate the generated speech on 3 metrics: voice quality, speaker similarity, and the emotion conversion ability. We use subjective evaluation to evaluate our results. The listening tests are conducted by hundreds of workers on Amazon Mechanic Turk. The result is compared with 2 baseline models: a simple linear F0 conversion system and the neural network model VC-StarGAN. We choose 4 emotion pairs with significant differences: angry, happy, neutral, sad. The result in the upper figure. For example, in the trial, angry to neutral utterances with label angry in EmoGAN were converted, and the generated speech was labeled by the majority vote of human annotators. We compute the percentage change from the source domain to the target domain. Higher value indicates stronger ability of emotional conversion. Our model is slightly better than VC-StarGAN regarding the emotional conversion ability, from 48% to 44%, and speaker similarity. One reason is that VC-StarGAN is designed for voice convolution among different speakers, while our model learns the entangled representations that can decompose the emotional characteristics and speaker identity. There are some sample audios on our website. For example, the original speech with emotion neutral.
You're a considerate fellow, there's nothing wrong in that.
And here is the converted speech with emotion angry.
You're a considerate fellow, there's nothing wrong in that.
Here is the conclusion. We developed a non-parallel emotional speech conversion system. It uses an autoencoder model to modify the spectral sequence, keep linguistic content and speaker identity, change the emotional style. There's no need for paradata, transcripts, or time element. And future works is to include the duration conversion and develop a general model for unseen speakers and train a larger corpus like the YouTube videos. Thank you for listening to my presentation. If you have any questions, please email me at jian@nyu.edu. Thank you.